Welcome back, everybody. Today we're going to keep thinking about line integrals, and we're going to introduce a new idea called a vector field. You might have been wondering when those were going to show up, and we're going to introduce what these are, and also think about line integrals and what that means in the presence of a vector field. But to recap, where we were last time is we saw that we have a nice catchphrase that allows us to see how a line integral is going to translate in terms of a parameterization of the curve. And this catchphrase works whether we're thinking about just a standard line integral where we have some information about a curve, and the standard line integral, right, just goes through and computes the net area of the ribbon that we get attached to our curve from our function information. The catchphrase works there, and it also works if we're computing one of these projected line integrals, where we're more or less computing the net area of the shadow or the projection of our curve onto one of our axes. In this case, right, since we have dx, we're projecting onto the x-axis. Right, our catchphrase works in any of these situations, showing us how our integral translates. All right, and so to start thinking about vector fields, it turns out that from physics, a lot of this motivation comes. Vector fields in physics arise very naturally, and in fact, thinking about line integrals in the presence of vector fields arises naturally. And let's see that. We can see that in a few different cases. So for example, if we imagine if we have some mass that we maybe place at the origin of 3 space, well, thinking about gravity, the gravitation from this mass is acting on all the points around it. Right, and it's going to be pulling points that are closer to it a little bit stronger than the points further away, but it's trying to pull everything towards itself. And so if we wanted to, we could represent that by at each point in 3 space attaching a vector that shows the force from gravity that our mass is affecting on it. And so here we have longer vectors a little bit closer to the origin and shorter vectors further away. But in this case, right, because gravitation is always pulling towards that center of mass, they're all pointing in that direction. And so this is how a vector field can arise thinking about gravity. It turns out that the question of, let's say we have some particle in space and we started at this point and then we move it around and maybe it ends up over here. Physically, a question we could ask is, what is the work that's done in moving our particle along that path through this gravity field? And it turns out to answer that question, we want to compute a line integral. And so we'll be talking about that later on. So this is one picture of how a vector field can arise. It can also arise thinking about electricity. So if we have kind of 2 charged objects, we can represent the electric current or charge through vectors attached to each point. And also, we can think about velocity fields. Perhaps this is showing us the direction of a wind that's traveling. It looks like over the ocean here. And the size of the vector is somehow showing us how strong that wind is. But so in general, right, a vector field on a space is just where we have a vector attached to each point on that space. And besides these kind of physical examples of vector fields, I claim that we've already seen an example of a vector field through gradient fields. If you remember back to the hill when we were all pointing in the direction where our feet were pointing up the highest, right, at that point, we were a vector field, right? Each of our tummies was pointing in the direction of steepest ascent, and we were all standing up there, kind of giving a vector at, you can imagine, at each point in the xy plane. And in general, this works out, right? If we have a function, f of xy, its graph gives us some hill, right? And at each input point in the xy plane, say at this point 2, 1, we can ask what its gradient vector is there, and whatever that vector is, attach it to that point, right? And so it's going to be pointing us in the direction of steepest ascent, because that's what gradient vectors do, right? And so maybe this point over here will attach its gradient vector. That says the gradient of f, right? And this one over here, attach the gradient vector there. Maybe the point's a little bit closer to the kind of middle where the top of the hill is. Maybe those gradient vectors will be a little bit smaller, but they're all going to be pointing us in this in the direction of steepest ascent at that point. Right, and so from that, the gradient of a function we can actually think of as a vector field. In this case, if our function is 2 variables, it gives us a vector field on the xy plane. And just as a real quick example, let's look at a specific function. Here's a particular function, 2 variables, and its gradient field, just by taking the gradient of f, so the partial with respect to x goes here. It's 2xy minus 0, and then the partial with respect to y goes here. And right there, this is a vector field, right, attached to each point in the xy plane. This is going to spit us out a vector that we can attach there. So for example, if we plug in the point 1, negative 1, so 1 for x minus 1 for y, the vector that we'll get from this is what? So negative 2 to start, and then 1 squared minus, so negative 1 squared is 1, so 1 minus 3 is also negative 2. And so if we come down here, attached to our point here at 1 minus 1 would be the vector minus 2, right? So it would go minus 2 in the x and minus 2 in the y, and so it would look like this. And similarly, if we ask what the vector attached to 1, 0 is, plugging that in, what are we going to get? We're going to get 0 for the first component and 1 minus 0 for the second. And so attached to 1, 0 would be this vector 0, 1. So it goes 0 in the x and 1 in the y. And so that'll be the vector attached there. And you could imagine, we could plug in any other xy point in the plane that we want, and to each point we'll get one of these green vectors attached to it through our gradient fields here. So vector fields can come from physically meaningful situations like gravitation or electricity. It can come from gradient fields, but they don't have to. In general, a vector field is just some vector function like this. So here, this would be vector field F, say on 3 space, right, on the XYZ space, we just need some way to, when we plug in a point in 3 space, XYZ, to get our X, Y, and Z components for our vector, right? So we just need some functions in here, some scalar functions to tell us how this works, right? And we could literally, just plug in some random functions if we want. I just made this up, right? You can make up your own if you'd like, right? And so whatever we plug in there will get attached to each point of vector. And so, maybe this isn't what that vector field looks like, but something like this, right? Just some abstract vector field where to each point in 3 space we have a 3-dimensional vector attached to it. Now, it turns out that vector fields that are gradient fields actually have some really nice properties. And so because of that, we like to give vector fields that are gradient fields a special name, and the label that we give them is conservative. So we say that a vector field is called conservative if it is a gradient field. So in other words, our vector field f hat is conservative if there's some scalar function f whose gradient field is the one we're talking about. Right, and in that case, this little function f is called a potential function for our vector field. And so yeah, it turns out that these types of vector fields, these gradient fields, have nice properties, and we'll see an example of that next time. What I'd like to do is go back now to thinking about more physically meaningful vector fields, and let's talk about the information that one might care about in the presence of such a vector field. So, here I have in 2D a picture that's supposed to be like a gravitation field, right? So we have some object, its center of mass is right at the origin, and so the gravity is acting on each point in the XY plane and looking to exert some force and pull it towards the origin. The points a little bit closer to the origin are getting pulled harder than those further back. And we mentioned that a physically meaningful question is, hey, if we have a particle over here, well, what's the work that's done in moving that particle along the curve? And it turns out that the information that we want to add up at each point along our curve to answer that question is the tangential component of the force vector there. That's the information that we want to think about to answer this physically meaningful question. Well, what does that mean? Well, let's add that to the picture here. So as we move along our curve, you can imagine at each point we can have a little unit tangent vector attached to that point, showing us the direction we're moving as we go. And so, for example, attached to this point here, we can have a little unit tangent vector, right? That is a capital T. That slides along with us. And what we mean by the tangential component of the force vector there is that we want to grab the amount of this vector f that's in t's direction. We want to kind of come down orthogonally and figure out the length of this bar that we get in t's direction from projecting this vector down. And so we can imagine doing that at each point. At each point here, say for example, at this point, we'll have a different unit tangent vector. And similarly, up here, we'll have another unit tangent vector. And at each point, we want to play this game and find the tangential component of the force vector there. Now, it turns out there's a nice formula to get a hold of this. In order to find this tangential component, this information that we are interested in adding up, all we have to do is actually just take the dot product of our force vector and our unit tangent, f dot t. It turns out that that gives us the tangential component. And so here on this note, I'm adding a little bit of detail here. The information that we're interested in is not just the length of this bar here, but actually its signed length. And the idea is that in a situation like this, where the bar is facing the same direction as our unit tangent, right, and that came because our f vector here was kind of going the same general direction. Well, in that situation, we're going to count that length as positive. However, if you look at these other two situations, if we project, say, this force vector orthogonally onto the line that our unit tangent vector gives, right, the bar we get, this tangential component, is actually behind us. And similarly here at this one, if we project orthogonally, the bar is behind us. And in that case, when our f vectors are pointing the opposite direction and the tangential component lies behind, that length is going to be counted negatively. All right, so our information is actually the signed length. That's exactly what this f dot t hands us. And so because of that, because of this being the meaningful information that we want to compute with our line integral in the presence of a vector field, we make that a definition. We say that the line integral of this vector field along our curve is the line integral over our curve where we add up this information that we care about, the f dot t. And so what I'd like to do at this point is just make a few notes about an integral like this, and then we'll look at an example. So to start, the first note I want to make is that the value of this integral here, this line integral, it actually depends on the direction that we parameterize our curve. So for example, if instead of moving kind of from the bottom to the top here of our curve, if we switched gears and we're moving from the top to the bottom, well then, for example, at this point, our new unit tangent vector would actually be pointing us in this direction. And so the tangential component that was in our same direction is now behind us. And indeed, at every single one of these points, things are going to be flipped. And what was positive is going to be negative and vice versa. And so essentially what happens is that if we move along our curve backwards, then we'll get the negative of what we would have gotten if we had just gone the original direction. Next, let's talk about how we can actually compute this line integral. Well, it's a line integral, right? And so we can compute it using our catchphrase, right? Our little mnemonic device here that shows us how line integrals translate. And so let's work through what our catchphrase shows us here and see that there's a nice simplification that happens. All right, so here is our line integral of our vector field. And using our mnemonic, right, we're going to multiply by 1 over dt dt. All right, and let's assume that we've parametrized our curve with a r hat vector function, say starting at a for t and stopping at b. Right, then here's how this integral translates, right? Just from exactly what we're seeing over here. We still have f dot t, and then we have ds dt. And recall, ds dt, right, that's the rate of change of distance. And so that is speed. In other words, the size of the velocity. So we have the size of r prime there. Check this out. I claim that there's a nice way to write our unit tangent vector as well in terms of our parametrization. Well, how we can do that is by, first of all, taking the derivative of our parametrization. That's going to give us a tangent vector. Like maybe that's shooting out way far in the direction we're heading. But if we want to get the unit tangent vector, well, we just need to scale this thing by its size, right? So r prime divided by the size of r prime. But notice what happens here. The r prime up top and the r prime at the bottom cancel out, and what we're left with dot producting against the f is just r prime. And so this is the nice simplified form that our formula takes here when we translate line integral for a vector field. And as usual, right, we still need to do our substitutions where we see x, y, or z or whatever, swap them out for what they are in terms of our parametrization. And now, because of this nice simplification that always happens, we write our line integrals for a vector field usually a little bit different than this kind of raw form. And the notation we'll often use is the integral over our curve C of f dot dr. And it might look a little funny, but I claim that this is an awesome shorthand notation because our mnemonic, our little catchphrase, still points us the right direction and tells us how this thing translates. All right, just go along with me here. If we follow our catchphrase and multiply this by 1 over dt dt, then what we're staring at is exactly what we need to be computing, right? F dot, the derivative of our parametrization with respect to t. And that's exactly what this is. So our mnemonic still works. All right. Let's now check out an example and see how this works out in practice. All right, so here we go. Let's compute this line integral for a vector field f, where the vector field f takes this form, and c, our curve, is this quarter circle, right? So starting from the bottom and moving to the top. And so here, right, on our picture, we don't see our vector field. We don't need to in order to work this out, but let me just mention, if we were to sketch on what the vectors look like from F, they would more or less be looking like this, kind of pulling down and to the right. All right, so this is what our vector field F would kind of look like. This is a somewhat rough sketch, but it gets the idea across perhaps. And one note I want to make right away is that because of this picture, if you trust me, then we can actually at least feel out the sign that we're expecting for the value of this line integral. Specifically, notice that as we move along this circle from the bottom to the top, these green vectors are kind of mostly pushing against us. And so because of that, we should expect most of our tangential components to be negative. And so we're expecting at the end of the day that the line integral for our vector field should be negative, just showing us that we're kind of fighting against the wind. Okay, that's just kind of a little side note for fun. If we just want to get back to business and compute this line integral, well, we compute it the same way we'd compute any line integral. Right, we have two steps. We need to parameterize our curve and then translate our integral, right, using our catchphrase. And so here, since this is a nice quarter of a circle, to parameterize our curve, I think polar makes a lot of sense. Right, the description of this circle here, right, that outer edge we're moving across, is just given by r equals 1, right, since the radius of our circle is 1. And the angles we're using, well, we're wanting to start at theta equals 0 and move up to theta equals pi over 2. So that's our polar description, right? In order to get our x and y, right, we'll use our kind of translation formulas. Plugging in r equals 1, we get 1 cosine theta, 1 times sine theta for our components, right? Just cosine theta, sine theta. All right, so that's step 1. Now let's go ahead and translate our integral. And so what I have here is just the line integral that we're starting with. And again, if we're wondering, well, how do I actually compute this? The answer comes from the catchphrase. I can't remember. What's that catchphrase again? Multiply by 1 over dt, dt. That's right. All right. And notice here, right, our t, our parameter is theta, right? And so that's what I have over here on the left. Derivative of our parameterization with respect to theta. And here we have the limits for theta. And here now we can just start substituting in what we have, right? So here I've just copy pasted our vector field from way up at the top of the page. Just scroll up for a second. There it is. All right, so just copy pasted our vector field. And over here, we just need to take the derivative of our parameterization. Right? So cosine becomes negative sine, sine becomes cosine, and here is the derivative here. And so here's our dr d theta. All right, now to kind of work this out a little bit more, we just compute the dot product like we would any other two vectors. Right? Multiply the x components and add what we get, and we multiply the y's. And so here we're going to get x squared times negative sine for the first term here, and then minus xy times cosine for the second. And so here's what that dot product becomes. Right, when we take the dot product of two vectors, we don't have a vector anymore, we have a scalar. And so we want to be careful not to keep any sort of vector symbolism around, right? We just have the scalar function now. And at this point, right, we want to kind of make things consistent. Here, this integral is with respect to theta. And so let's get any of our other variables swapped out. X and y, in terms of our parameterization, right, that's what we use to swap them out. X is cosine theta and y is sine theta. And so using our parameterization to replace those, x squared becomes cosine squared, and x becomes cosine. There is another cosine there, and so that becomes cosine squared. And then y becomes sine. And actually, nicely, these two are the same, and so we can collect this as negative 2 cosine squared theta sine theta. And at this point, the dust has settled, and pop quiz, what could we use to integrate this kind of Calc 1 integral that we are left staring at? U sub, right? Absolutely, right? We have the nice kind of cosine as our inside function, and its derivative more or less floating around outside. So U sub with U equals cosine should be very helpful, and I'll let you work through the details. This is what we end up with, negative 2/3. And notice, just from a little side note before, the negative makes us happy. That's what we were expecting. Things, at least from that perspective, seem correct. All right. Well, that's how it looks to take a line integral for a vector field. Parameterize our curve and then translate our integral, right, just like we would any other line integral. And what I'd like to do to wrap up today is take this exact same situation, but give you a chance to work through this, thinking about getting a parameterization a different way. Specifically here, we grabbed this parameterization thinking in terms of polar, but we could also, if we wanted to, describe this curve using rectangular. All right, so the idea here is that our curve is actually the graph of a function of x, right, and of y, it turns out. But maybe let's just think about it as a function of x, right? For each x, there's just one point on our curve. There's one y value corresponding. And so we can actually use x as our parameter. Why don't you pause the video, take a few minutes, and see if you can construct your parameterization, and then use the catchphrase to translate our line integral for our vector field and see if you can get to the same result that we got the first time around. All right, so let's talk through this one here. To parameterize, to get our vector function, r hat is going to give us our points x, y. If we're using x as our parameter, that can stay. We just need to know what y is, and we can grab that from our equation here, solving our equation for y, and using the fact that we want the top half, get root 1 minus x squared, and so we can plop that in for y, and there we go. There's our vector function. We just need to answer the question, what x's do we want to use? And notice here, because of the direction we're moving along this curve, we actually want to start at x equals 1, right? And then move and stop at x equal 0, right? We're actually moving from right to left along our curve. So if you did 0 to 1, flipping the limits will just essentially give what you got as your result, but with a negative out front. Yeah, so we do want to pay attention to the direction that we're moving along our curve. That'll affect our starting and stopping values for our parameterization. But once we have that, once we have our parameterization on hand, ready to go, we can go ahead and translate our integral. And again, just using our mnemonic, multiply by 1 over dt. And so over here, we just need to remember what our t is, right? So we're thinking about x is our parameter, and that is our t. And so this becomes dr dx. And taking the derivative here of our parameterization, we get 1. And the derivative here, we got a little chain rule to work through. This is what we end up with. We can then take the dot product of our two vectors here. We end up with this. Lastly, we need to get this y in terms of our variable x here, and using our parameterization to swap out what y is. And so making that adjustment, y becomes root 1 minus x squared, and notice, very happily, that cancels out with the square root in the denominator. We're left with x squared plus x squared, so 2x squared, and we can very quickly integrate and see that we do indeed get that same negative 2/3 that we got above. Okay, good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.